to have a sense for all those solubility rules, and D is, I just got messed up. I was grading somebody's paper and I circled D, but actually E is the right answer. The solubility rules for, I think most sulfides are insoluble and most hydroxides are insoluble. So zinc sulfide and copper 2 hydroxide would be insoluble. Question 2, which of these is Kp and Kc equal? So you would be looking for the change in number of moles is equal to 0, and D fits that bill where we have 2 moles of gas and 2 moles of gas. Okay. Question 13, it gives you an equilibrium, and it asks, let's see. Oh, it gives you equilibrium concentrations in terms of partial pressures, and asks for the Kp. So I know it's a little messy, but let me see if I can do this. So right here is my Kp expression, where since the stoichiometric coefficients are 1 across the board, basically it's the partial pressure of the products times each other divided by the partial pressure of the reactant. And so you get 1.2 times 10 negative third, which corresponds with B. Moving on to the next page, so question 4. Maybe. Okay. Question 4 is which of these KSP expressions are correct for the solubility product of magnesium phosphate? So you can see what I did here is I took magnesium phosphate in equilibrium with 3 moles of magnesium cation plus 2 moles of phosphate anion. So the one that corresponds to that is actually C. Magnesium raised to the 3rd power times phosphate raised to the 2nd power. Question number 5, large equilibrium constant, and before I even read the distractors, and some of you guys do this too, I came up with what I think a large Kc means is that actually will favor the formation of products, so B is the best answer there. Question number 6, which of these following statements is always correct? And actually 1 and 2 are always correct. It's always correct that the product concentrations will appear in the numerator, and it's always, if they appear at all. And it's always correct, too, that if you have a high K or Kc or Kp, then actually that will favor the formation of products. So D is the best answer there. Question 7. Which of the following reactions? Let's see, what was it? So for this equilibrium, and it gives the Kp, what is, given that one, what is the equilibrium, the Kp for the 2? So actually the relationship between equation 1 and equation 2 is reversed and times 1/2. So then actually you can see what I did here was take the inverse of Kp1 and also raise to the 1/2 power. So 1.15 is the new Kp for that second equation. Question 8. Write the Kc expression for this equilibrium. So again, it's the product raised to its stoichiometric coefficient divided by the reactants, each raised to their stoichiometric coefficients. Of course, that means the ammonium is raised to the 4th power, so that corresponds with E as the best answer there, or the only answer there for question number 8. Question number 9. Write a balanced chemical equation given this KSP expression. So of course on the product we have Fl minus and hydronium cation, and on the reactant side we have HF. But to balance it, we're going to add 1 H2O molecule here on the reactant side. We've been talking about that, haven't we, in Unit 4. So C actually corresponds to the best answer for that one. Question 10, which of these following statements concerning equilibrium are constants are true? And the only thing that's true is 2, that they very much depend upon the temperature. The Kc or Kp or KSP is for a particular temperature. Okay, question 11. If you were given the solubility in terms of grams per liter of lead 2 chloride, you were supposed to come up with the KSP. So that actually, you can kind of see where I doodled lead 2 chloride in equilibrium with the lead 2 and the 2 moles of the chloride ion. That means the KSP expression is molar concentration of lead 2 raised to the first power times molar concentration of the chloride ion raised to the second power. And in this case, I had to take the 4.4 grams per liter and get it in terms of moles per liter using the molar mass of PbCl2. So notice when the dust finally settles, it's 0.016 molar in lead 2, and it's twice that, 0.032 molar in the chloride ion. Then we can just go ahead and substitute those concentrations into the KSP expression. So the KSP for lead 2 chloride is 4.0 times 10 to the minus 6. So the best answer there is A. Question 12 was probably one of the more interesting ones, the multiple choice. So given the overall equation of interest right here, N2 plus O2 goes back and forth with 2NO, and given the 1, 2, and 3 you see above it, can we manipulate 1, 2, and 3 to get the overall equation of interest, or equilibrium of interest? So notice for number 1, we leave it the same. For number 2, we take it times 1/2. And for number 3, we reverse it and take it times 3. So in doing that, I went ahead and did that over here on my answer key. And remember, so like for instance, for number 2, since we took it times 1/2, that means we need to take the K2 raised to the 1/2 power. For number 3, since we reversed it, we have to take the inverse of it, and since we took it times 3, we have to take that times 3. And then remember that if we have these Ks for like K1 prime, K2 prime, K3 prime, the overall reaction of interest, the K can be gotten by multiplying them together. So you do end up getting E is the best answer for that one. Question 13 then. Like this. So given that equilibrium between I2Cl2 and ICl, and the fact that it is exothermic with a negative heat of reaction, if you decrease the temperature, what is going to happen? So in this case, you can see since it's exothermic, I put heat here on the product side. So since we're decreasing the temperature, actually we are removing heat, so it's like a pulling sort of effect. But we said that since it's a pulling sort of effect, your product is going to increase, so I wrote the KP expression down here. And what that means is you will get a new KP, and your new KP is going to be higher than your old KP. So E is the best answer there. This one right here, the second part, is worth 2 points apiece. So not only did you have to say what would happen to the Cl2 concentration, but you also had to say kind of why. So if we add more moles of BrCl, of course BrCl is the product, and so Cl2, the reactant, will increase. If we remove BrCl, BrCl is the product, and it's kind of like pulling, and so actually we would have fewer moles of Cl2. The Br2, actually, since it has a cute little L next to it, means it's a liquid, and it does not appear in the Kc expression, so no effect. Increasing the just general pressure of gases inside the vessel will have no effect. E, if we increase the partial pressure of BrCl, that's the same thing as increasing the moles of BrCl, so we're pushing it to the reactant side, so you'll have more Cl. Question F, if we double the volume, okay, it will favor the side of the equilibrium that has more moles. So actually the side that has more moles is the product side, with 2 moles on the product, 1 mole on the reactant. So actually that, since it favors the product, it will decrease the amount of Cl2 there. And last but not least, what about the temperature? So the fact that it is an endothermic reaction, if we lower the temperature, then basically we're going to be removing, it's like removing a reactant, and so it's actually going to form more Cl2. So lowering the temperature will result in more Cl2 being formed. Okay, the next problem was one of these where I give you some snapshot concentrations of everything, and you're supposed to say, is it at equilibrium? And if it's not at equilibrium, which it wasn't, which direction does it need to go? So from the equilibrium constant expression, of course, is right here. And we can plug in, we can turn that into reaction quotient, plug in our molar concentrations of everything, and we get a QC, reaction quotient of 9.2, which is clearly less than 6.9. Since that's the case, it's not at equilibrium, and it needs to go to what I say the right, or form more products to reach equilibrium. The fourth question. Kind of stepwise, the first part A and part B were both worth 1 point, and C was worth 6 points. So write an exchange reaction, and so actually down here I wrote a little picture of what we've got. We've got 70 mils given this molarity of barium chloride. We've got 45 mils given this molarity of sodium sulfate. So the exchange reaction is when we end up with barium sulfate and sodium chloride. And balance it needs to put a coefficient of 2 in front of the NaCl. Then B, you were supposed to say with the barium sulfate is basically insoluble. What does that equilibrium look like? And that you can see for B. So then you were supposed to say, will a precipitate be formed? And remember, we were given the KSP. Okay. So first off, you need to get to the molarity of the barium concentration and take the volume, its molarity, get to moles. We're going to divide that moles by the total solution volume, which is 115, which is your 70 plus 45. So that's the molarity of your barium cation. Get to the molarity of your sulfate, kind of similarly, using the volume and molarity of the sulfate, getting the moles of sulfate and dividing that those moles by the volume, which is 115 milliliters, to get the molarity. Yep. And then we plug into the equilibrium, the KSP expression, and basically get a reaction quotient, which is 1.42 times 10 to the negative fourth. And since that is larger than the KSP, oh, there it is. The KSP is 1.1 times 10 to the negative 10th. Then a precipitate will form. So on to the next one. Okay, so I have a little picture up here. You were given masses of masses. You had to read this a few times. I think this threw some of you all off. It says initially it contains a certain mass of CO and a certain mass of H2. It switches gears at equilibrium. It has a certain mass of methanol. And so actually down here, I went ahead and got the initial molar concentrations of the two reactants. Excuse me, where'd it go? And then the equilibrium concentration of the product. Okay. So we need an ice table for sure. So this is one of those where you were given the initial concentration of everything and the final concentration or equilibrium concentration of one thing, and you could do an ice chart kind of by deduction, get to Kc. So here's my ice chart. The initial concentration of the two reactants, their molar concentrations. Initially we had no CH3OH. Notice that the stoichiometry is a 1 to 2 to 1 relationship. So the fact that I had this, you guys kind of did this in lab, the fact that the molar concentration of the CH3OH at equilibrium was 0.0520 molar, then I kind of backtracked. That means the change was 0.0520 molar. And then these two things are decreasing, so we could apply a negative change. The fact that stoichiometry between the CH3OH and H2 is a 1 to 2, that means 2, it loses, or there's a change negative 2 times 0.0520 molar. For the hydrogen, we can actually apply that and get a real number. The change for the CO actually is just minus 0.0520 molar. So these three are equilibrium concentrations, so we can plug those back into your equilibrium constant expression and knock out a value for Kc. Okay, the next one. So in this one, this is the one where you didn't have to take it all the way to solve for x. So this one says we've got 10.5 grams of the reactant, and that's it. We're going to let it decompose, and the Kc is given. So you needed to get the molar concentration of the NO using the mass the volume of the container, which is 2 liters, and the molar mass of NO, which is 30.01 grams per mole. So it starts out with 0.175 molar NO, and nothing of the N2 and nothing of the O2. Because of the stoichiometry, if we let X be equal to, X be equal to the amount of N2 and O2 formed, then that means minus 2X is actually the change in our NO because of the coefficient of 2 in front of the NO. So we can go ahead and get equilibrium concentrations by taking the initial, applying the change. Okay, so those are equilibrium concentrations in terms of X. The last thing you needed to do just to finish up was to plug the equilibrium concentrations back into your KC expression. And then you were done. Notice that this one, actually, we could have solved it without using the quadratic, recognizing that since we have basically what, x times x is x squared, right? And this is quantity squared. Actually, you could take the square root of that thing is equal to the square root of that thing, and things would kind of fall into place kind of nicely. But so for the next one, you were supposed to come up with the molar solubility for this salt, both in water and where you had a common ion effect. So I did the ice chart for both of them. You wouldn't really have to necessarily for the in pure water. But copper 2 hydroxide, the equilibrium would look like that. The KSP expression would look like this, where copper 2 times the hydroxide ion squared is equal to the KSP, which was given. In this particular ice chart in pure water, notice that we don't have any common ion, okay? So basically, the KSP is equal to x times 2x squared, and KSP is given. Then we need to kind of manipulate that to get to value for x, which is the molar solubility. So do a few things, and the molar solubility then is equal to 1.8 times 10 to the negative 7th molar in pure water. So then if we go ahead and change it up, sprinkle a little bit of, actually instead of water, the liquid we have waiting is 0.050 molar magnesium hydroxide. One of the things you need to recognize, since hydroxide is our common ion, that if that's the molarity of the magnesium hydroxide, since we get 2 moles of OH minus for every 1 mole of MgOH2, the molar concentration of the hydroxide ion is 0.100 molar. So our ice table looks very similar to up above, but now we have the common ion. We have the hydroxide ion concentration is not 0, it's 0.100 molar. So if we apply the simplifying assumption that we talked about in class, and we will be talking about another simplifying assumption with acids and bases coming up, the fact that if the amount that ionizes is if x is pretty small compared to 0.100, then basically this term right here becomes 0.100. And so then our KSP expression becomes this. It's the molar concentration of the magnesium, which is x, times the molar concentration of the hydroxide ion, which is approximately 0.100 squared, and that's equal to KSP. So solving for x, you can see that the molar solubility is 2.2 times 10 to the negative 18th, which is appreciably smaller with the common ion already in there. Then last but not least was the fractional precipitation question. So basically, I didn't draw a picture for this, did I? You're going to add sodium iodide dropwise to something that has 2 cations in it, silver and the lead 2, and the molar concentrations of those are given. So basically, your sodium in sodium iodide is along for the ride. It's your I- that's going to actually potentially form silver iodide and lead 2 iodide. So one of the first things I did was to go ahead and write, and you really didn't have to do this, but show it ionizing. That's the first step up there. But probably what you did need to do was for those two salts of interest, I think you probably need to go ahead and write the equilibrium or the solubility product constants. Solubility equilibria, I guess is what it is, for those 2 possible salts. So I came up with an iodide threshold for both of them, solving for basically in the KSP expressions, solving for that and that in both cases. What was the threshold to get silver iodide? 4.2 times 10 to the negative 13th. What was the threshold to get lead 2 iodide? 2.3 times 10 to the negative 2nd. And so as you can see, the silver iodide doesn't take much iodide in it to go ahead and precipitate out. So it's going to come out first. Then, I got 2 A's, don't I? So for the second part, or part B down there, it says, so once you're, if that one's going to come out first, the question goes like this. How much silver, would you have when your lead 2 iodide starts precipitating out? So if we turn our attention to the threshold for the lead 2 iodide, the iodide concentration is 2.3 times 10 negative 2.3 times 10 negative second molar. If we plug that in for our iodide concentration, of course that's the KSP for your silver iodide, we can come up with the silver ion is going to be present in an amount of 3.6 times 10 to the negative 15th moles per liter.